Hey, it's Mr. Belanger. So let's take a look at a classic quadratic problem. And it's usually about maximizing the area of a rectangular or square enclosure. And you can use a quadratic equation actually to do that. So sometimes what students struggle with is the concept on how to do that. So let me go over an example. So the question could be, what is the maximum area for a rectangular enclosed space with three sides? Sometimes it'll be all four sides, sometimes it's three sides, maybe it's up against a wall or a river or something like that. And I'm going to use 24 meters of fencing. I'm like, okay, let's actually just draw this out for a second. So this is my side that I don't use here. Maybe, like I said, maybe it's a river or something. And there's my rectangle. I drew three examples. So let's come up with three examples that could possibly work. There's lots of examples. So I could potentially say, well, this side is 1 meter and this side's 1 meter, because clearly they'd be the same. And that would leave me with 22 meters left over for the length. How about this one? These two sides could be 2 and 2 of length, which is obviously 4, and leaving me with 20 left over here. Or how about a 5 and a 5, which is 10, leaving me with 14 meters of fencing left over here. These are all possibilities, right? And of course, if I wanted to find the area, we all know it's length times width. I could do that for all three of these examples, and you can see that I'm getting different sizes for the area, right? So it matters like how you build the fence if you want to maximize the space. But the question is, I don't want to do this all day long. That's ridiculous. Until I find I have to look at every possibility. Don't need to do that. That's why we have other things, right? And that's what you can do with a quadratic. So you have to think about this. A quadratic is a parabola. A parabola is a U-shaped graph. And sometimes they arch up like a rainbow, and sometimes they make it like a giant U. In this particular example you'll see in a moment, it has to be a quadratic that arches like a rainbow because the vertex will be at the very top, which we would call the maximum point. And since I'm finding the maximum area, that's what I'm actually looking for. But how do I get the quadratic? Well, you need an equation, and that in this case is going to come from the only two things that I possibly know about this situation: area and perimeter. And I know that area of any rectangle or square is just length times width. So here's my picture again. I'm just calling it x, x, and a y because they're unknowns, of course. And length times width in this case can also be x times y. And the perimeter of this object would be when you add up all the sides, of course. And so that would be 2x's plus only a single y. And if it was a four-sided figure where I'm using all of the four sides of a fence, well, then I would say it's 2x plus 2y. You make the adjustments where you have to. Okay, then what do I do with that information? Well, you take those two equations and then you simply blend them together. They substitute into each other. And that's very simple. You simply take, in this example here, I could take this y and isolate it. So I move the 2x, I took this 2x right here and I moved it over beside the 24. That's why it says 24 minus 2x. That should be equals y. And then I'm able to substitute this value, which equals y, into the area. So instead of now x times y, I'm replacing the y with 24 minus 2x. That is the rearranged portion of the perimeter formula. It's a really simple thing. We've all substituted before. I'm just taking one equation, rearranging it, and then plunking it in the other equation. Okay, so then area equals x times y, but that is now x times 24 minus 2x. I expanded it, I changed it around to a more familiar format, and look what I have. There's a quadratic, there's the x squared. Oh, that should say 24x, my bad. And that negative 2x squared, that is indicating, that's the a value, that this is a quadratic pointing down. So that's what I wrote here. This is a quadratic that points down, so if I was to graph it, it would look like this. And that point right there is a maximum point. It's the maximum vertex. That solution is going to lead me to the answer to this problem because I'm trying to maximize this area. Okay, well, then the question is, how do I find a vertex? Well, you just complete the square. And so that's a basic skill. I'm not going to go over that here. So I completed the square right in here. And then eventually you could see that I wrote down the vertex and I had positive 6 and then 72. Now, you got to be careful. Sometimes people get solutions and they don't know how to interpret the solution. This is the x value. This is, of course, the y value. In this question here, look what I have. I've got area equals and then my x value. That x value is the x that I called the side of the rectangle. Oh, so it's 6. So that's 6. But be careful. Don't, this 72, I know it's a y value, but in this equation right here, it represents area. It is impossible for it to be the y value along the bottom, right? It's not this. I got 24 meters of fencing. How could I possibly call it 72? That's ridiculous. It actually represents the area because this is in the position of y right here. Okay, you got to use common sense about this. And then, so then all I did was rearrange that down here and say, right, okay, there is my rectangular enclosure. It must be 6 and 6 because that was the x. That makes 12. Leave me 12 over for the bottom, and 6 times 12 is 72, and that was the area. Okay, I hope that helps with your questions about maximizing the area of a rectangle. Good luck.